Okay, in this video, we're going to do a quick overview of inverses. First, we have to talk about one-to-one functions. A relation is a function if every input has exactly one output. We already know that. Special kind of functions called one-to-one, and that's if every output came from exactly one input. Every x goes with exactly one y. It goes back and forth. Okay, a one-to-one function is like a marriage. You can have as many friends as you want, but you can only have one spouse. If you know the x, you know the y. If you know the y, you also know the x. So imagine there's been a murder in Savannah. You're a detective. You want to find out who the murderer was. You find a blood sample on the floor that somehow you know came from the murderer. Can we determine who the murderer was from the blood sample? Well, is blood type a function? Does every person have a blood type? Yes. Every person has a blood type. The inputs here are people. The outputs are blood types. That's a function. Is it a one-to-one function, though? If you know the blood is A positive, do you know who it came from whom it came? No, not necessarily. A bunch of people might have the same blood type. Blood type is not a one-to-one function. What about DNA? If I know the DNA from the blood sample, can I trace that back to the person? Yes, that's a one-to-one function. Every person has DNA. Every DNA came from only one person. One-to-one functions. If you know the input, you know the output. If you know the output, you know the input. The way to check this graphically is the horizontal line test. We know we have a function if we pass the vertical line test. One-to-one functions also pass the horizontal line test. So y equals x squared is not one-to-one. It's a function. Vertical line test is good, but it does not pass the horizontal line test. Like example, look here at 4. Two different inputs, -2 and +2, give me an output of 4. If I tell you y equals 4, you can't tell me exactly what the x value was. X cubed, on the other hand, is one-to-one. If you know the output, you can trace it back to the input. Passes both vertical and horizontal line tests. A circle is not even a function. Can't be a one-to-one function if you're not even a function. This doesn't pass the horizontal or vertical line test. Okay, inverses. This is what we're trying to build to. One-to-one functions have inverses. They can be undone. A one-to-one function has a buddy function called his inverse that undoes everything he does. That's what an inverse does. It undoes the function. It does all the opposite stuff in the opposite order. I like to say like socks and shoes. You get up in the morning, you put on your socks, then you put on your shoes. When you get home at night, to undo that, you don't take off your socks first. If you're going to undo something, you have to undo it in the opposite order. You have to take off your shoes first, then take off your socks. Okay, some properties of inverses. If a function's one-to-one, it has an inverse. One-to-one functions have inverses. They can be undone. We write that inverse like this. This looks like an exponent, but it's not. That is not a power of -1. This means you've got some function f. This guy here is f inverse of x. Some properties here. If you know f of a equals b, then the inverse is going to undo that. It's going to go backwards. It's going to take that output b and bring you back to a. Another way of saying that, it's the exact same information here. If you know a point on the graph of f of x, a point AB, then the graph of f inverse will have the same point just swapped. All we do is swap the x's and y's. The point BA will be on the graph of the inverse. Another way of saying that, all this really says the same thing. If you compose a function and its inverse together, everything will completely cancel out, leaving only behind the identity function x. So f composed with its inverse is x, and this has to work both ways. You have to check both ways. F inverse of f of x should just cancel out and leave behind x. Okay, an example. I claim these two functions are inverses of each other. We get f of x is 2x minus 7. G of x is x plus 7 over 2. We should just be able to look at this and see if they're inverses. They should do the opposite stuff in the opposite order. Okay, so let's look at f. Say I wanted to throw in an x value. I wanted to plug in x equals 27. Doesn't matter. What would we do? We would take 2 times our input and then subtract 7. That's what f does. F takes your input, multiplies by 2, then subtracts 7. If I wanted to undo that, if I wanted to go backwards, instead of subtracting 7 at the end, I would add 7 at the beginning. Instead of multiplying by 2 at the beginning, I would divide by 2 at the end. Opposite stuff in the opposite order. Okay, let's check this algebraically and see if they are in fact inverses of each other. Let's look at one particular number. F of 4 would be 2 times 4 minus 7. 8 minus 7 is 1. G then should take that 1 and go backwards and give me back the 4 that f started with. With g of 1 would be 1 plus 7 over 2. 8 over 2, it is 4. F of 4 was 1. G of 1 comes back to 4. That doesn't prove they're inverses of each other. Just because it happens for one number doesn't prove anything. To prove they are inverses, we have to show that when we compose them, f of g of x gives me x, and I have to check it both ways, g of f of x equals x. Okay, well, f of g of x means rewrite f twice input minus 7, but now instead of writing x, I write what's in the parentheses, all of g of x. So f of g of x is twice g of x minus 7. Hey, look here, we could cancel the 2's, get x plus 7 minus 7. And hey, look, the 7's cancel, leaving just x. Does that prove they're inverses? No, it has to work both ways. I have to also check g of f of x. G of f of x means write g, but now instead of writing x plus 7 over 2, I write whatever's in the parentheses, f of x. I write the entire function, f of x, right here. So f of x plus 7 over 2. Hey, look, those 7's cancel. I get 2x over 2. Hey, look, the 2's cancel. I just get x. If you do, in fact, have inverses, this is what will happen every time. Everything will just telescope and cancel out, leaving behind just x. So since this worked both ways, we do, in fact, have inverses. F and g are inverses of each other. So we could call g here f inverse, or we could call f g inverse. It doesn't matter. Okay, if you graph a function and its inverse on the same set of axes, they will always be symmetric about the line y equals x, because all they do is swap all their x and y values. The x's from one function are the y's from the other. The domain of one is the range of the other. So here's f, here's g. You notice that if I take f and just rotate it around the line y equals x, I would get g. The line y equals x will always come right down the middle of a function and its inverse. Okay, finding inverses. So somebody hands me a function f of x and wants me to find the inverse of it. Here are the steps we do. First thing we do, instead of writing f of x all the time, it's just let's be lazy. Let's rename f of x y. Then we replace all the x's with y's, all the y's with x's. Swap out all the x's and y's. And technically we're done. That's the inverse. But we like our functions to be functions of x. So then we'll go through a little bit of algebra and solve for y. And then rewrite y as f inverse of x. It should be down here. Okay, an example. We've got this function. F of x is x minus 5 cubed plus 2. Before we try to find the inverse, we should make sure this is in fact a one-to-one function. Hey, we know how to graph that. That's just x cubed shifted 5 to the right and up 2. Over 5 up 2, there's our graph. That is in fact a one-to-one function. It passes both horizontal and vertical line tests. Okay, the first thing we do is replace f of x with y. We just don't want to carry that f around. It's less writing to write just y. Okay, next we're going to swap the x's and the y's. Every place you see a y, replace it with an x. Every place you see an x, replace it with the y. So we get this. That y became an x, that x became a y. From this moment on, my goal is to solve for this y right here, get y by itself. So I have to make all this other stuff go away. Whenever you're solving, you know how to do this. Start out and work your way in. I want to make the 2 go away. It's added, so I'll subtract it. I want to make this cube go away. So to do that, I'll have to do the opposite of cubing something, the inverse of cubing, cube rooting. And then finally, to make the 5 go away, it's subtracted, so I'll add. Okay, so first, we get rid of that 2. So move the 2 to the other side by subtracting it. Now we're going to get rid of this cube by taking the cube root of both sides. We're allowed to do that. Remember, with square roots, you need plus and minus on one side. That's because x squared is not a one-to-one function. X cubed is a one-to-one function. I don't have to worry about that. I can take the cube root of both sides. And in fact, the cube root of junk cubed is just junk. This cube root and this cube will cancel each other because they're inverses. That's what inverses do. They cancel each other. So on the right side, I get just y minus 5. On the left side, there's nothing I can do with that. I just get cube root of x minus 2. Remember, my goal is to get this y by itself, so I got to make this 5 go away, add the 5 over, and now I'm done. Here's my inverse. Just rename it now. F inverse of x is cube root x minus 2 plus 5. Okay, just so you remember, here's our original function. Our original function was a cubic. His inverse is a cube root. Hey, that's not surprising. Here, in the original, I was subtracting 5 inside. In the inverse, I'm adding 5 outside. In the original, I added 2 inside. In the inverse, I subtract 2. Let's say that again. In the original, I added 2 outside. In the inverse, I'm doing the opposite, subtracting 2 inside. A function and its inverse do all the opposite stuff in the opposite order. And we can look at the graph. Here's the graph of the original, f of x. The cubic shifted over 5 up 2. Here's the graph of his inverse that I decided to call g here. This is the cube root function, scooted over 2, up 5. And you can see here, right through the middle of them, is the line y equals x. Any point that's on this graph, like say the point 5, 2, is reflected on the other graph by swapping the x's and y's. Over here we have the point 2, 5. The domain of the original is the range of the inverse. The range of the original is the domain of the inverse. Okay, that's function inverses. I'll post some more videos that should be popping up right now where I do some more examples, but that's the basic of everything.